Hello everybody, and welcome to the Percentiles and Standard Scores lecture. So, first of all, who is thinking that they can do this equation? Well, guess what? By the end of this lecture, or today, you will be able to, I promise. So, to this point, what can we say? Well, let's think about this scenario. A boy says, I got a 98 on my math test today. Mom says, that's very good, son. You must be very happy. And the boy says, yes, but there were 200 points on the test. Mom says, oh, I'm so sorry. I guess you didn't do too well. Boy says, yes, but I got the second highest score in the class. Mom says, very good. And the boy says, yes, but there are only two of us in the class. So how well did this boy actually do? Well, we're going to answer that in part today. So we know right now we can get means, medians, variance, standard deviation, etc. from, let's say, these 5 scores. But what if the rest of the population looks something like this? And this is a bit of an extreme example. But what do we take from this, where we have a mean so much higher, medians higher, variance much, much higher? What can we do? Well, we're going to talk about 3 different ways to think about these types of situations. So the first one, percentiles, then we're going to cover z-scores and t-scores. So percentiles are just easy ways to understand where an individual person is on a test. So a percentile is what percentage of the entire distribution was under that score. So if you were in the 75th percentile, that means the score was better than 75% of the population. And 33rd percentile means better than 33% of the population. This is easy to use when you have normally distributed variables. However, it's surprisingly difficult to calculate these by hand, so we're not going to be worrying about that. But you need to know how to interpret them. So let's move on then to our z-scores and t-scores. So what is more, being 7'2" or weighing 450 pounds? Well, again, this seems kind of like an apples to oranges comparison, and in some ways it is. But what we are going to be able to do is not answer that, but answer what is more compared to the average, being 7'2" or 450 pounds. Standard scores will allow you to address this question. It wouldn't necessarily be able to tell you what is more, 7'2" or being 450 pounds, but it can tell you compared to an average, assuming you also have standard deviations. So what standard scores really do is it makes scores interpretable across units. That's the key, across units. No matter what the unit is, height, weight, IQ, anything, standard scores are there for you. And 2 of the common types of standard scores are z-scores and t-scores, which is why we're covering them. So what is a z-score? Well, z-scores are calculated by taking a specific value. Notice there's no summation, so it's not every x, just a single x score, subtracting the average of x, and then dividing that by the standard deviation of x. It's pretty straightforward. Now, what do z-scores have in terms of properties? Well, all distributions of z-scores have a mean of 0. That's just how it is. So the average, if you were to take z-scores for everyone in the population, the average z-score would be 0. And z-score distributions have a standard deviation of 1. And this is because you're dividing by standard deviation. And then the last thing is, when you transform scores from from raw scores to z-scores, you're not actually changing the distribution of data. They're still distributed the way they were previously in their raw form. So if you were to have some distribution that was skewed prior to it, and then you do a z-scores, it's still going to be that way. So let's do a couple examples here. So if you had a mean of 42 and a standard deviation of 3, so mean 42, standard deviation of 3, you could figure out what a z-score is for any score, let's say 45. Well, in that case, it's going to be 45, your score, minus the average, which is 42. Then divide that by standard deviation, which is 3. So 45 minus 42 is 3. 3 divided by 3 is 1. So your z-score for 45, when the mean is 42 and the standard deviation is 3, is 1. Now, a z-score for a raw score of 39, you'd plug it in again. 39 minus 42 is negative 3, minus 3 divided by 3 is equal to negative 1. So 39 minus 42 equal to negative 3. Negative 3 divided by 3 is equal to negative 1. So what does it tell us that one has a negative sign and one has a positive sign? Well, over here, think about what this is doing. We are taking a score above the mean and dividing it by the standard deviation, and it's 1. Here it's a score below the mean. So really, all that the negative or positive sign tells you is if your score is above or below the mean. So 45 is above 42, so it's going to have a positive z-score. 39 is below 42, so it's going to have a negative z-score. So always and forever, if you have a z-score that is positive, it means that that score, the raw score, was above the mean, and if you have one that is negative, it means it was below the mean. Now, let's make a chart instead where we have a mean of 5 and a standard deviation of 2. If you were to go through the equation, you would see that 3 minus 5 is 2. 3 minus 5 is negative 2. Divided by 2 is negative 1. So each of these raw scores give you the following z-scores, assuming a mean of 5 and a standard deviation of 2. So what does this chart tell you? Well, z-scores, it turns out, are in units of standard deviation. So you will see that a score of 3 is actually one score below the mean. So this, because it's in units of standard deviations, it's one standard deviation below the mean. Notice that standard deviation is 2. 3 is 2 below 5. So it is one standard deviation, which is 2 units, below the mean. Alternatively, 7 is 2 above 5. Well, 2 again is the standard deviation, so it is one standard deviation above the mean. 5, on the other hand, 5 minus 5 is 0, so the z-score is 0. Well, if the score is 0, that means that your score is the mean. How do we interpret these other two? Well, 4, if you want to go ahead and do the math, feel free, but 4 is 1/2 of a standard deviation below the mean. 1/2 of the standard deviation, well, if the standard deviation is 2, half of that is 1. 4 is 1 less than 5. So this is 1/2 a standard deviation below the mean. This is 1/2 of standard deviation above the mean. So how would we interpret these? Well, the exact same way. A raw score of 1.5, when you have a mean of 5 and a standard deviation of 2, is 1.75 standard deviations below the mean. A raw score of 5.9 in this situation is 0.45 standard deviations above the mean. A raw score of 7.8 is 1.4 standard deviations above the mean. That is how you will interpret any z-score. If your z-score is 10, it means 10 standard deviations above the mean. If it's negative 5, it means 5 standard deviations below the mean. So, think of this a different way. What is a z-score of a raw score that is equal to the mean? Well, the numerator is x minus x bar. So the mean, let's say it's 10. If your raw score is equal to the mean, that's going to be equal to 10. So 10 minus 10 is 0. So you're always going to have a z-score, that's the raw score, is equal to the mean, that's going to be 0. So the mean for all of your z-scores, if it is the mean is your score you are trying to reference, it will be 0. So what do z-scores tell you? Well, it tells you whether or not your raw score was above or below the mean. It does that by giving you either a negative sign or not having a negative sign. So again, if it has a negative sign, the mean was below, your score was below the mean. Whereas if it's above, that means that score was above the mean. And it also tells you how many standard deviations the raw score was above or below the mean. And this is how you can compare things across units. So let's say 7'2" was 3 standard deviations above the mean, and 450 pounds was 3.5 standard deviations above the mean. Well, that would tell you that being 450 pounds is actually greater compared to the average than being 7'2". This is how you can compare across units. So I'm going to give you these scores and ask you to pause the recording and calculate yourself the standard deviation. And then I want you to plug in 55 into the equation, subtract it from the mean of these scores, and then divide by the standard deviation of these scores. And when you are done, resume the recording and we'll walk through the solution. All right, so hopefully you've calculated it already. Here's the z formula. We have our z-score of the raw score being 55 minus the average, which is 50, divided by 4.81. Well, that's just 5 divided by 4.81, which is 1.04. So what does this tell you? It tells you that your score of 55 is 1.04 standard deviations above the mean. And that makes sense if we look at the numbers, right? 55 is 5 more. Well, your standard deviation is a little less than 5. So that means it's a little more than 5 above the mean. If you can't see how this works, please ask me. All right, so again, some of you will already get this, but just to be sure, what do you need? You need means, standard deviations, and then your score. So let me ask you another question here. Jot down on a spare piece of paper, whatever you're taking notes on, your happiness score from 1 to 5, where 1 is not at all happy, 5 moderately, 3 is moderately, and 5 is extremely happy. I know all of you have got to be a 5 because you're listening to this recording, but you might be different. And then your religiousness score from 1 to 5, where 1 is not at all religious, 3 is moderately religious, and 5 is very religious. So go ahead and jot those scores down. And then I want to see what you can say about yourself compared to other people. So these are scores from our data set that you guys helped create. So the mean for happiness in our data set was 4.08 with a standard deviation of 1.06. And for religiousness, 3.64 with a standard deviation of 1.37. So go ahead and use your happiness and your religiousness scores and plug it in with this information. So pause the recording, and when you're through with that, go on to the next slide. All right, so here is the table for all of the possible religiousness and happiness scores. So if your happiness was 1, that would mean you were 2.91 standard deviations below the mean. Whereas if your happiness was 4, you were actually 0.07 standard deviations below the mean. Now, how is that possible? Well, it's because our mean in happiness, again, if we go back and see, it's 4.08. So if your score was a 4, you were actually below the mean. Alternatively, for religiousness, if your score on religiousness, let's say it was a 2, that means you'd be 1.19 standard deviations below the mean. However, if you scored a 4, you're actually 0.26 standard deviations above the mean. And this is kind of peculiar to some people, but it means that a score of 4 in happiness is not equal to a score of 4 in religiousness, right? A score of 4 in happiness is lower than the mean, whereas a 4 in religiousness is above the mean. And this is the beauty of standard scores, is you can see compared to other people where you are, regardless of the units. Okay, so that's z-scores for us. And we're going to move on now to t-scores. And the reason we're making such an abrupt change is they're actually very, very similar. Z-scores and t-scores are basically tell you the same amount of information, the same things, but they're in different units. So for t-scores, they have a mean of 50 and a standard deviation of 10. So t is actually equal to 10 times your z-score plus 50. So what does this mean? Well, the equation that we saw at the beginning is actually what's going on here. This is a t-score equation. It's 10 times x minus x bar, the numerator, divided by standard deviation, plus 50. So you're able to do this equation already. You might not realize it, but we are already to this point. So some of you might be saying, this seems really easy. T-scores, you just take your z-score times 10 and add 50? Yes, it really is that easy. So what is your t-score for happiness and religiousness? Well, here is what the t-scores would be based on z-scores. So you can go ahead and plug in whatever your z-scores for happiness and z-scores for religiousness were and check them against this table. But you'll see that if you had a happiness z-score of 0.86, then your happiness t-score is 58.69. Similarly, if your religiousness score was negative 0.46, your religiousness t-score is 45.31. It's as simple as taking whatever your score was, multiplying it by 10, and adding 50. So again, who thinks that they can do this now? Hopefully everyone. Now, you might be asking yourself, why do we have these things? Well, this goes back to the last mini lecture on normal curve. Your normal curve, this nice pretty normal curve up here, is in units of standard deviations. So oftentimes people will have their z-scores and t-scores to tell you where people fall along the line on a normal curve. So if you have a z-score of 1, positive 1, that means that you are 1 standard deviation above the mean. And you can see how z-scores relate to percentile ranks and how they relate to t-scores. Now, you might be asking yourself, why in the world would anybody have a z-score and a t-score if the z-score tells you the same information as a t-score? It's just bare numbers. Well, it really is kind of convention in whatever field you are in. Sometimes people will use t-scores just because that's what they use as opposed to z-scores, but they do tell you the same information. The main thing z-scores will do is keep the numbers positive. Unless you're more than 5 standard deviations below the mean, you're always going to have a positive number. So some people like it because of that. You're also, generally speaking, not going to be dealing with like very small numbers. But z-scores have the advantage that interpretability, at least for me, makes a little bit more sense. If you're negative, you're below the mean. If you're positive, you're above the mean. That's a little bit more intuitive to me. You can also see how these scores relate to different types of, these are IQ scores. So IQ scores are such that 1 standard deviation is equal to 15. So if you were a z-score plus 1, that means your z-score would be 1, your t-score would be 60, and your IQ score would be 115. Those all tell you the exact same thing when it comes to IQ scores. This is the purpose of z-scores and t-scores. To give you an idea where people place on the normal curve And remember, the normal curve is just a commonly occurring distribution of scores. So if you are 2 standard deviations above the mean, your z-score is going to be 2, t-score is going to be 70. If you're 3 below the mean, z-score is -3, t-score is 20. So hopefully, at this point in time, you can see that z-scores and t-scores are all about referencing your score compared to the rest of the population on whatever it is, and units don't really matter. Normal curves look like normal curves no matter what it is: height, weight, IQ, anything. That is what we're doing with z-scores and t-scores.